Welcome back, Algebra Express. We have just a couple more lessons. So today we are in Rockswold 5.5. So in Rockswold 5.5, we are going to go over more properties of logarithms. The last time we introduced logarithms, before that we introduced exponentials. So we started with exponentials. We defined logarithms as being the sort of inverse of the exponential function. And in this one, we're going to work a little more with logarithms. And then in the next one, we will start doing equations. So I believe we're going to do exponential logarithm and exponential and logarithmic equations in the next section. So in this one, they have a few things that they want us to figure out on the calculator. So if we do log 5, and you put log 5 in your calculator, and you say plus log 2, you might notice that gives you 1. And going back to how you get log of 1, if we don't see a base here, this is a base 10. Okay, and if you do this one, I'll give you a few seconds to put this in the calculator and do it. This should give you 2. And if we look at this one, and I want to review last time, if we have a base 10, we're getting log of 10 to the first. If we look at this one, this would be log of 10 squared, or maybe we're getting log of 100. This would be log of 10 to the third, or you could say log of 1,000. So how am I getting that? How am I getting 10 from 5 and 2? How am I getting 100 from 25 and 4? And how am I getting 1,000 from 205? That's what they're wanting to know. Okay, so what they want you to notice is that you're adding 2 logs. And so if we add 2 logs, addition on this outside is like we're going to multiply the things on the inside. So this would be like log of. So if we're adding 2 separate logs, addition on the outside is like multiplication on the inside. So when adding 2 separate logs, we're going to multiply what's inside to combine. To become 1, we multiply the thing on the inside. What about subtraction? So now they want you to do subtraction. So we do log of 20. We type log of 20 in our calculator and we do minus log of 2. What is that going to give me? That's going to give me 1. This is going to give me, if I do log of 500 minus log of 5, do that thing right quick in your calculator. That should give you 2. And so if we're adding, it's like we're multiplying on the inside. If we're subtracting, again, we're getting to log 10 here. How we get 10 out of 20 and 2? We have to divide those things. So this is like log of, getting that from, I'm doing log of 500 divided by 5. Adding 2 logs on the outside, we're on the inside. And here they want you to find 2 log of 3, so this is not going to be an even number, so I guess I got to do this in my calculator. So 2 log of 3 is going to give me somewhere and I'm going to have to probably approximate it. This is going to be 0.9542, something like that. If I do log 9, it should give me the same thing. What they're wanting you to recognize is calculating. They should give you the same thing. 3 log of 2, that's not going to be the same thing as 2 log of 3. It's going to be point, and now I'm rounding again, 903. 1. And if I do log 8, what they want you to notice is that it should give you okay. So this one might be a little trickier. How am I getting from 3 to 9? And what is happening to this 2? So if I think about getting from 3 to 9, I had to be like multiplying it by another 3. So it's sort of like I'm doing 3 squared. If I look here, if I go from 2 to 8, it's multiplying by 4 is one way to think about it, maybe. But what I'm doing is I'm taking 2. 4 is 2 squared, so what I'm doing is adding two more 2's is another way to look at it. But I am taking 2 to the 3rd is going to give me 8. So what is the rule? Coefficients on the outside can be exponential. But part of that is because we have the properties right here. So this was the thing we just figured out. We could do this with log base 10. 5 and 2 was the first example. If I have 5 and 2, I'm going to multiply 5 and 2 together on the inside of the log. So addition on 2 separate logs on the outside is going to be multiplication on the inside. And so one way people describe log is logs are the algorithms of exponents. They are the algebra of the exponents. So if we look at these, they should have analogous sort of exponential properties here. These are the exponent properties, just looking at them from a different sort of direction. And so we did talk a little bit about this first one. These are the 3 new rules that they're introduced. We talked a little bit about this first one in the last section. So if we look at log of 8 equals 1, log of 8 of 1 equals 0. It's kind of a weird operation, but if I want to exponentiate things, that's what they call it. So what I'm going to do is I'm going to let this be my exponent on an a variable. And if I do that, what you might notice is I have a to the log of a. That is an inverse. So this is not doing anything. What I'm really interested in is what I plugged into that log to begin with. So where I end up with on this side is something like 1, and this is a to the 0. So going back to our exponent properties, we know if we raise anything to the 0 power, it's not 0. So we're assuming a is not 0. It's a non-zero number raised to the 0 power. It is going to give me 1. Okay. The other side of that is if I take a log of 1, I should be always getting this 0 back. And so this is the other side of this same property. Okay. These other properties, we've had these properties before, just maybe not in the way that you see them here. So if I think about what a of log a of m, log a of n, a of log a m n. And so this is the property that says if we're adding exponents, Another way I can rewrite this side over here is I have something that looks like a of log a of m. If I'm adding exponents, I can think about this as sort of doing it the backwards direction. I had two like bases. And so this was the rule that said if we have two like bases, we can add the exponents. And so this is the rule that kind of verifies this thing happening. And so if we simplify this out a little bit, we notice that this side gives us mn and this side is going to give us mn. It's going to hold true that this thing is equal. But this is the other side of the looking at the rule that says if we are adding two exponents, or if we multiply two like bases, we are adding the exponents. So addition on the outside is multiplication on the inside. In this one, if we did a similar sort of approach, this would be the thing that tells you if you are dividing two like bases, you are subtracting the exponents. And this one is sort of like we're raising exponents to exponents. If we can do similar sort of properties here, we will be invoking that whole thing like that. Exponents to exponents, we multiply the exponents. So now these are like our exponents to exponents are getting multiplied. Okay. So there are two sort of directions we can go. This is an equal sign. So we could start with, this is an equal, these are all equal signs. We could start with a single log and we could break it apart into more logs, or we could have multiple logs and try to get it into a single log. So we're either going to expand or try to contract it to a single log. In the first one, I believe we are trying to make a single log out of these things. Okay, so we have two separate logs. We want to evaluate these things. This is a log base 7. So I would want to look at the previous chart. If we are subtracting two logs, it's like we take the things on the inside and divide them. So I am taking 2 and I am dividing it by 98. And so sometimes if we can contract it to a single log, it might be easier to solve than solving them kind of separately. Here you might be looking at log 7, 2 over 98. That doesn't look a lot prettier, but if we reduce this fraction, you might be able to see it a little better. If we divide 2 by 2, we get 1, 98 by 2, we get 29. This is like we have a log base 7. 49, we want to think about these as being powers of 7. So we can go 1 over about as far as that. So what that is telling me is that this is a log of 7 to the negative 2 power. 1 over 7 squared is 7 to the negative 2 power minus 2. Okay. If we look at log 6 log 8 of 2. Okay. So this is which rule? We want to look at that previous page. It's not the first rule. It's not the second or third. It's got to be that last rule that they're giving us there. So this is if I have coefficient, I can take that coefficient and I can put it as a power to the thing that's on the log. So what this tells me is if I have a coefficient, here's my coefficient 6, I can take this thing and raise it up and I can put it as a power on this thing. So what now I have, okay, so there are a few ways to simplify this. I think the easiest way is probably just to calculate 2 to the 6. So 2 to the 6, that's going to be 64. If you want to keep on and don't know what 64 log base 8 of 64 is, that's fine. Logs the other day. Here we go. Log base 8 of 64. 64 I can rewrite as 8 to the second power. If that's true, then this is just the number 2. Okay, and with this next one, I want to look at this property. And so what property am I using on this one? -2 log base 9 of 3. So you might notice this is still one log. It's not that first property. So it's got to be that last property, number 4. So what I want to do is I want to take this and I want to raise it as an exponent of the thing inside the log. -2. So maybe a little bit of evaluating on 3 to the -2 and what that is might help you get it in log base 9. So 1 over 3 squared is what 3 to the -2 is. So log base 9 of 1 over 9. And there's really only one other thing. You could probably get it from here. 1 over 9 is 9 to the -1 power, or this is just going to be -1. So there probably are a few different ways you could probably solve this thing, if I'm being honest. There are things that are going in the right direction and some things that are definitely going in the wrong direction, right? To being able to solve this. But, or not solving, we're not actually not solving things, we're simplifying. Sorry, so I should probably be specific on that. Solving is like when we get a quantity for a variable. So this, we are just simplifying things. We're rewriting this term a little bit differently to be able to evaluate it by hand. So we're using properties to condense things into a single log so that we can evaluate it by hand. That's what we're doing. Another way I see maybe is if you want to do, instead of -2, you might be able to break that up into -1 and 2. So if you didn't want to take the negative, this might have been a little quicker. We do log base 9 of 3 squared, which is 9. So this is just a -1 and a log base 9 of 9, which will give us -1 times 1, which will give us -1. So there are probably sort of multiple approaches that you can take. And they should all be able to get you there if you're doing the correct sort of thing, right? Okay. So this you might want to pause and think about this for a minute. What do we have going on here? Log base 2 of 4 to the 18. So we have been using this property and we have been using it in one direction, but the beauty of this thing is that it is an equal sign. And an equal sign is also known as a biconditional because it goes both ways. So when we use an equal sign to talk about a property, I can go from left to right, but I can also go from right to left. So if I have something that's being raised to some crazy exponents, I can pull those crazy exponents down. So if I want to do that, that might help you solve this one a little bit quicker. So I definitely don't want to try to do 4 to the 18th. That's going to rack my brain. So let's try to bring this thing down. So what this is going to end up doing is having 18 times log base 2 of 4. And now if we look at this, this should be a little bit easier to evaluate. Log base 2 of 4. If I want to rewrite 4 as the base 2, it's 2 squared. And now I'm looking along here, log base 2 of 2 to the 2. Oh man, you got an option of 3 numbers to pick there. Hopefully you're looking at that one and bringing it down. Important you pick that 2, not the other 2. 18 times 2 is 36. All right. And we get one last problem to practice with. Ooh. I don't know why they put these. Oh, maybe a bit more. They put them in bold. Okay, so I see why they did that now. These have multiple logs. So these have 2 logs. These have multiple logs. So there are 3 logs here. There are 3 logs there. So we can take these properties and we can expand these properties. We're doing it with 1 or 2 logs right here. We can do this with multiple logs, and we can condense multiple logs. Okay. So on this one, what property do we want to use? That is not, I think I give us a half power in there. Square root of E. Okay, so the first thing I want to do is probably rewrite that square root of E as E to the 1/2 power, I'm guessing. I don't think I keep the square root of E. That's kind of annoying. We hadn't gone over rationalizing denominators, and I think we're going to end up having to do that here. But if I want to use my log properties, I see these 2 things subtracting. What is the rule? I want to combine these to 1 log. If things are subtracting on the outside, I have to divide them on the inside. So it's the first thing, 5e squared divided by 5 square root of e. And I think we could, yeah, writing it as a half power will work pretty well. So if I want to look at this, this is 5e squared. I'm going to rewrite this thing as 5 to the 1/2 power, or e to the 1/2 power. If we look here, these 5s, 5 over 5, these things will simplify out. This I want to do 2 minus 1/2. So if I do 2 minus 1/2, do my exponent rules to do subtraction here. This is like e to the 1/2, so I can do 1.5, or I could do maybe 3/2. And so when I look at this, I get ln, I get e to the 3/2. So these 2 are inverse operations. This is like a log base e, and this is like an e to the power of something. And so what I end up getting here is the 3/2. Okay. Now we have multiple terms. So we have something log base 8 of 6 plus log base 8 of 2 plus log base 8 of 5. If you want to go 2 at a time, do these in the order that they are presented. That is fine. So if we look at log base 8 of 6 and log base 8 of 2, and we ignore this log base 8 of 5 just for a second, we look at these two. If I want to combine these two, I combine them to one single log base 8, and I multiply 6 times 2. So this is log base 8 of 12 plus log base 8 of 5. And this is log base 8 of, and now if I want to combine these two, addition on the outside is multiplication on the inside. So this is 12 times 5 on the inside. So this is log base 8 of 60. Okay. And we don't go over the change of base formula until later. So this, after you get to here, we have condensed this thing to a single log. I believe that was what the instructions were. This is fully simplified. So I cannot simplify this into base 8 of anything. If I'm thinking about bases of 8, I'm thinking about 8 and 64. And 8 to the third is what, 512. So I should be thinking about multiples of 8. Already 8 squared is going to be 64. So this is already between 8 and 64. It is not going to be an even log. We don't go over the change of base formula until later. If they wanted an approximation, we could give them an approximation. And so your calculator might be able to do this without the change of base formula. It may not. But if we want an approximation, I'll give you a 4 decimal. Let's do 5 decimal because it's a little bit easier. I can get around it to zeros. 1.96896, somewhere in that ballpark is what it should be giving you if you can do this in your calculator. And we'll go over how to do this in just a second. So some calculators allow you to just throw them in there with different bases. Other calculators don't. A lot of calculators only have log base 10. Sorry. Oh, there's none on here. Sorry. The regular log base 10, or they have ln. Some of them have different bases. So if we're looking at this thing, order of operations when we do these things is important. So we want to condense these things to a single log. So if we start subtracting and adding, what you might notice is we have to do subtraction before we do addition. So when we do PEMDAS, we do addition and subtraction. They take the same priority. We do them left. And so what you want to do is you want to combine these through the subtraction before you do the addition. Before we even start adding and subtracting, if there's any coefficients here, we probably want to get rid of those coefficients. If we go back and look at rules 2 and 3, they do not have coefficients on the log. So if we're going to invoke rules 2 and 3, we have to get rid of our coefficients. Rule 4 tells us how to get rid of our coefficients. So I'm looking at this thing. I'm seeing ln of x minus ln of 2x plus 2 ln of y. And this last guy is the guy that I'm talking about. So I don't want to touch these two things, but this last one, if you see a coefficient, you can raise it as an exponent. So this is plus ln of y squared. And again, maybe you don't see it right off the bat. Maybe you combine these before you do that. There are different orders that you can do these things in, right? Okay, so now I'm looking at, I want to just focus on these two things. So if I want to combine these two things into a single log, my log looks like a single log. If I'm subtracting on the outside in order to combine on the inside, I'm going to have to do some division. So what I'm dividing is x by a 2x. And then I have to add ln y squared. So this is ln. If we want, we could simplify this thing now. But we have an x over an x. So this is an ln of, and don't forget there's like a 1 coefficient up here. So this is like a 1/2. And we want to add ln of y squared. Okay, so now we want to combine these two logs. How do we combine these two logs? We combine them to one log. What we do is we multiply the things on the inside. So this should be ln of 1/2 y squared, or y squared over 2. Same thing, right? ln of y squared over 2. If you want to put the y squared on top, that's fine. Okay. And we have combined things. They are into a single log. This has variables in it, so you're not even going to be able to really evaluate this, right? We have to give you a value for the variable to even evaluate it. So that is fully simplified as it's going to get as a single log. All right, so one more example, and then we are going to start talking about the change of base formula. So it is something that should hopefully go pretty quick. We condense things to a single log, and now we want to go the other way. Okay. So when I look at this thing, what I am sort of seeing in my mind is like I have like this thing on top, and I have this crazy thing on bottom. But the thing that really sticks out to me there is that big division bar. That is the first thing kind of separating things here. So if I want to take care of this division bar, it is a single log if I'm dividing on the inside of the log. I want to split this up. I want to make this into multiple logs. So division on the inside is going to be subtraction on the outside. So this division bar is the first thing I'm taking care of. The thing on top of my division bar looks like x plus 1 squared. The thing on the bottom looks like a square root of y and a z squared plus 1. So there are probably 3 things that I should be looking for inside the log to expand it. Division, the other thing is multiplication, and then the other thing is exponents. So now we have it here. I want to look log by log. If I look at this log, do I have division, multiplication, or exponents? If you said multiplication or exponents, I think you might be on track. If I have exponents, the rule for exponents is if I have exponents, I can bring them down in front as a coefficient. So 2 log of x plus 1 is just by itself now, taking care of that square. This looks like minus. And this is subtracting this thing. If I'm looking inside here, I want to see if there's multiplication, division, or exponents. It looks like there's multiplication and exponents, but if I'm looking at this multiplication, is the first thing I want to take care of here. Now, this is the one where you have to be careful. So this is log. If this is multiplication, this is sort of like addition of two separate logs. And this is exactly where you have to be careful, because if you do this, you're probably going to miss it. When I subtract this log, I am subtracting this entire thing over here. So I should put definitely some parentheses around this side somehow. This first one looks like the square root of y. This one looks like z squared plus 1. Okay, so this is 2 log. And if I look in here, do I have any multiplication, division, or exponents? Does not look like it. I just have an x plus 1. And I'm subtracting this. If you want to distribute this, you can. You don't necessarily have to. I'm going to rewrite this as log of y to the 1/2 power. Because I know in the book they're probably going to do that. We haven't really gone over too much about writing radicals as fractional powers. But doing square roots is like we have y to the 1/2 power. I'm going to distribute the subtraction, so this should also be subtraction. If I'm looking in here, and I look at multiplication, division, or exponents, if I'm looking at exponents, I have an exponent, but it is just on the z. So if I have like z squared plus 1, I want to be able to pull out an exponent from this entire thing. The exponent is not on this entire thing. It's just on the z. So I cannot pull out this exponent unless it is on the overall thing. So I'm going to keep this as z squared plus 1. All right, so there's one other thing I can do. This is an exponent. I can bring down my exponent down in front. But this should be fully simplified. This is fully simplified. This is fully simplified. This is fully simplified. So we're looking at the thing, the argument inside the log. We're making sure it doesn't have any multiplication, division, or exponents that we can pull out. This doesn't have any multiplication or division. It has an exponent, but it's not an exponent we can pull out. It's like it's being attached to this, and this guy doesn't have an exponent on it as well, right? He's kind of by himself over there. Okay, so we want to do a calculator check. So log of 64. So log of 64 should be between what? 1 and 2, should be between 10 and 100. So if we do log of 64, it's going to give me 1 point, and they want to do 3 decimal places, what, 806. I'm going to do ln of 3. 1.099. So throw them in your calculator right quick. Log of 64. We round it to 3 decimal places. Basic calculator check. Okay, so now for the change of base formula. So you might notice, and like I said, this differs by calculator. You have a log and you have an ln key on your calculator. So they are down here, log and ln. Most calculators, scientific calculators, will have the log and the ln. They do not all have all these crazy bases, like log base 2 or log base 20. So how do we figure out things that are in different bases? The quick story is big log over little log. So they're giving you this in different bases. But basically what we're going to do is we're going to convert it. And they say log b. We're going to use log base 10 most of the time. So you can do log of x over log of a. You could also do ln. It really doesn't matter. We're changing the base. So you could use either key on your calculator if you wanted to. But long story short, it is big log over little log is what a lot of people will say. So we take log of the big number, which is 12, and we divide it by log of the little number, which is 2. Don't, that is not your exponent property, if that's what you're thinking. That's division on the outside. We wouldn't want to look at division on the inside. So I know it's like maybe a little bit confusing there. We just went over that. That is not that property. It is different. What does this tell me? I have 3.584. So we did it with log, and I mentioned it, but we could do it with any base that we want. We're changing the base here. We can do ln of 12 over ln of 2. It should give us the same number because we're changing the base. 3.58, then went 3 decimal places, 3.585. We do the same thing, log 2 over log 20. This should be a really small number. 3 decimal places, 0.231. We do this by doing log 2 over log 20. Big log over little log. That's what a lot of people say. Okay. And on to the last few examples. On these, we're just basically plugging these into a calculator and getting a decimal approximation. So if I want to do 2 times what, log 10 over log 7, and subtract log 4 over log 3. Two times 1.833, 1.1, minus 1.26, somewhere in that ballpark. So I'm rounding it to 4 decimal places, and then I'll round it to 3 in the end, probably. So 2 times 1.1833 minus 1.2619 gives me 1.10, and I'm going to round that up to 5. All right, so last thing, we want to take a square root of log of 14 over log of 2. So if I do log of 14 over log of 2, I'm doing the square root of 3.80735, somewhere in that ballpark. I'm probably just going to recall the answer on my calculator. Is the easiest way to do it without rounding. And so this is giving me something around 1.951 if I want to do 3 decimal places. Okay, so this is just seeing, I guess, if we can do this in order of operations, if we can get a good round number. Okay. So that is the final problem on here. I will see y'all soon.